Hi, this is example number 6 of section 14.1.2.3, and we are talking about the conservation of energy. The arm is pulled, this arm right here is pulled such that S is 100 millimeters. So you can imagine that the pull, that the ball is pulled back, so and the spring is compressed 100 millimeters and release. When it says release, it starts from rest. So remember that we have to really carefully read every word to be able to solve the problem. So the spring is unstretched at S equals 0, and all surfaces are smooth. And we are asked to find the speed when the ball that the ball is at 0.3 meters, so they are telling us the mass, kilograms, and the speed when the ball is right here at theta equals 60, and the normal force between the ball and the surface. So we will apply, in this case, the principle of work and energy. But since we have any non-conservative forces, so we will have conservation of energy. That means that we will have the total energy, which is the kinetic energy plus the potential energy in position A, will be the total energy, which is kinetic energy and potential energy at B, at these two positions. So this is the principle of conservation of energy. So we start, since the ball is released from rest, our kinetic energy at point A is equal to 0. Then the potential energy at B. So we have gravity, right? So we will have the potential energy due to gravity plus the potential energy for the spring. For the gravity, we always put a reference that we will use for both positions. In this case, I will put the datum or my reference in position A. So my potential energy due to gravity is equals to 0 for that position, and then I have the potential energy of the spring for that position. The spring is unstretched for S equals 0, but I have here S equals 100 millimeters. So it means that the spring is compressed. So I do have potential energy for the spring, and the energy will be the constant. Do I have the constant of the spring? I should have it. Let me see. Yes, I have the constant of the spring. Sorry that I did not write it. 1,500 newtons over meters. That must be something that is given. We have to have the description of our system. And delta will be 0.1 meters. I will work in consistent units, so I will convert millimeters to meters. So I have these two values, and then I have kinetic energy at B. I will have 1, and that's actually what I'm looking for, right? Because they asked me to find the speed of the ball at final position, which is B. So that's something that I want to find. So that will be 0.3 times the velocity that I want to find. And the final potential energy at position B will be, I don't have a spring anymore, so it will be only due to gravity. And here, since my datum is, I will use the same reference, I have to find this distance. This height is what I have gained in potential energy. To find that, that will be positive mg. So this is 1.5 minus 1.5. So the whole distance is 1.5 because this is the radius of that circular path. And this distance is 1.5 cosine of 60. Okay? And of course, gravity is given, and the mass is given. So that will be 1.3 times 9.81 times 1.5 times 1 minus cosine of 60 is 1/2, right? So it will be 1 minus 1/2, which is 1/2. So I have all the values, and as you see, the only unknown is the velocity of B. So if I plug all these values, so I plug in kinetic energy plus potential energy equals to kinetic energy plus potential energy. One-half. So, and then solve for, I'm going to solve for B, velocity at B, and then I get that the velocity of B is equals to 5.94 meters over second. So that's the solution. So we found the speed. And the second question that we are asked to solve is the normal reaction. For the normal reaction, we have to do our kinetic analysis. So I will do my free body diagram of that ball in that position. And then I have the weight. So my weight is always m times g. And I have the normal force. We have to decide which coordinates we want to use. As you remember from chapter 12, we have different possibilities. We have a cylindrical coordinate system, we have normal and tangent, and we have Cartesian coordinates, right? So which one will be here the best option? Definitely, if we see here, the motion is tangent and normal. So I'm going to be using normal and tangent component to be able to describe my equation, where this angle right here is 60 degrees. So this is my free body diagram, and I have also the kinetic diagram, right? The kinetic diagram will involve my mass times tangent acceleration in my tangent direction, and my mass times normal acceleration. Since I want to find the normal force, I will add forces in normal direction. So add forces in normal direction, and I have to just make those two diagrams equals. The free body diagram equals to the kinetic diagram, and I have normal force minus weight times, right, cosine of 60 will be equals to my mass times a normal acceleration. And as we remember, the normal acceleration, cosine of 60 is 1/2, so I can actually also just substitute the numbers that I have. This is 0.3, this is 9.81, this is 0.5, right? And this is 0.3. And the normal acceleration, as we know, is velocity v squared over the radius of curvature. And the radius of curvature is 1.5. So as you see, velocity of v we already have. We plug that velocity in v over here with velocity v equals 5.94. I can solve for n. N is equals to, solve for n, and then the n will be equals to 8.53 newtons. So here we use first the conservation of energy to solve for the velocities, and then anytime that we have forces involved, using the kinetic analysis is the best way to go.